Hey everybody, and welcome to Chapter 17 entitled Equilibrium, the Extent of Chemical Reactions. Alright, if I'm going to give any advice throughout the semester, it is understand this chapter as soon as possible, because the basics here in Chapter 17 are going to be used in Chapter 18, 19, 20, and 21 as well. We're going to use Equilibria in 5 chapters throughout, I can't ever see my thumb, 5 chapters throughout this semester. So get Equilibria down, and then it'll be much easier when we're learning new material a little bit later on. All right, well, our first podcast here in Chapter 17 is going to be the establishment of Equilibria. Like, how do we get Equilibria, and what do we kind of define as being Equilibria? In order for us to begin to think about Equilibria, let's take a trip back to Chem 1 material. In there, we probably discussed the equilibria established between a liquid and a vapor. So here I have a bottle of water. This bottle of water, you can see there's some water in here, and up here there is some area that doesn't have any liquid water in it. But up here there is some water vapor that is sitting up here. All right, now, this water bottle has been sitting in my garage for at least 2 years, right? And I can guarantee that when I put it in there, the liquid level was right here, just like it is today. That hasn't changed. All right, however, what is happening is that some of that liquid is evaporating. But at the exact same time, some of the vapor that was up there is actually then condensing back in the liquid phase. And they're happening at the exact same rate. Right? And so we say that this reaction is reversible. Right? We're going, not only is the liquid evaporating, as we can see, it's going in the forward direction, but the gas is condensing, which is going back in that reverse direction. We showed that as these reversible arrows there. Right? And so both of these processes are taking place at the same rate. And so overall, the amounts don't change over time. Right? That liquid level is going to remain constant, right, until I open my bottle of water. All right, in this chapter, we're going to focus on gaseous chemical equilibria as I teach this to you. But I want you to understand that we can do this for things that are aqueous as well. So at the top here, notice that I have a generic equation, which we talked about the fact that we're going to see this generic equation like this again and again. From our previous chapter, we saw one that's like this, where I have some number of compound A is going to react with some number of compound B and so on, and we have this equilibria. And again, this could also be A of A, and this could be aqueous plus B of B, aqueous, and so on. Right, so this could also be applied to aqueous things as well. Right, so just keep that in mind as we go through the chapter, that anytime we're doing gaseous stuff, that we could be doing this for things that are in the aqueous state. All right, so notice that if I wanted to talk about this system, right, we could talk about this system by each one of their partial pressures, because the pressure of the overall system would equal the pressure from gas A plus the pressure from gas B plus the pressure of C and the pressure of D, right? Remember that the overall pressure is the sum of all of our pressures. And if we use our ideal gas law, right, notice that the pressure of one of those species, right, this could be A, B, C, or D, is equal to the number of moles of that same species times RT over V. So that's telling us that the pressure of our species is directly related to the number of moles of that same species, right, which is basically what it says down here on the bottom. The example that I have chosen, and the reason that I chose this example is because this textbook and the last 5 textbooks I've ever taught out of have always used this example, is dinitrogen tetroxide and nitrogen dioxide equilibria. Right? And so the reason that we picked this is because the N2O4 is colorless and the NO2 is brown. And so when we only have N2O4, we can't see the gas. When we have NO2, we can see that the gas has turned brown, and so we see a color change occur. And so that is one way that we are able to determine which gases are present. So it says then that when our N2O4 is sealed in a container, right, we start out with it being colorless, and over time a reddish-brown color develops. All right, and that is because we are decomposing our gas into that nitrogen dioxide. And that happens by the equation that is shown down here. All right, well, what is happening is that the N2O4 is decomposing, right? It is going to decompose to form nitrogen dioxide. But as the nitrogen dioxide starts to build up, some of those nitrogen dioxides can then collide with each other, right? Remember those collisions that we saw from the previous chapter. They can collide together, and when they do, they can form our dinitrogen tetroxide, right? That's our reverse reaction taking place. And we are going to form equilibrium, all right, when the rate of the reaction in the forward direction, when the rates are equal. All right, big note, that does not mean that the amounts of each one of them are equal. It just means that for every time an N2O4 is decomposing at the exact same rate, right? Rate being from our previous chapter, at the exact same rate, two NO2s are colliding to make another N2O4. And so the amounts don't change over time. It doesn't mean that the amounts are the same. It just means that they don't change over time anymore. So here we have a figure showing that in part A over there on the far left side, that is our pure dinitrogen tetroxide. Notice that it is a colorless gas. In the middle, we would have pure nitrogen dioxide, which is a brownish red gas. And on the right is when we have a mixture of both of them, right? And so our equilibria, notice that the color is kind of a mixture in between the two of those two things. And so the reason that we chose this as our example is because we can physically kind of see those changes. So that leads us to, how are we establishing our equilibria? All right, well, we started with only the N2O4, right? And so if we think back to our rate of reaction, right, if we start with a lot of that, then the rate of it decomposing is going to start out fast. But if you think about it, as you're decomposing some of that, right, then the concentration of it is going to start to decrease, which will mean that the rate of it decomposing is going to start to slow down. That all comes from when we learned about the rate of our reactions, right? Well, at the same time, right, the rate of reaction of our NO2, right, them colliding together to form N2O4, that reverse reaction, that's not going to happen very quickly, because at the very beginning, there's going to be very few, right? Not much NO2 to begin with. But then it's going to start to, right? We're going to be building up more and more NO2, and as we build up more and more of it, right, that rate increases. Right? As we get more and more of them, there's going to be more likely that they're going to collide together. More of them are going to, have enough energy to overcome activation barriers and stuff like that, right? And so we're going to have that reaction happening faster. And so what we have to get to is, right, the rate of our forward reaction and the rate of the reverse reaction. Once they equal each other, right, then we have equilibrium. And a lot of people do this by showing like arrows. Like if we think about it, right, to begin with, the rate of our forward reaction is very fast, and the rate of our reverse reaction is slow. And then after time, the rate of our forward reaction slows down, and the rate of the reverse one is going to start to speed up, and the rate of our forward keeps slowing down, and then eventually like the rate of our reverse is going to equal that. Well, once we reach that point, now we are at equilibrium, right? When those rates are the same as each other. Well, here we can see a data representation of what we're talking about here with the establishment of our equilibrium. So notice that, right, and I don't know why in the world they make figures like this, but we are going to say that at time 0, right, we have the pressure of N2O4 is 1 atmosphere. So for some reason, this right here is 1 atmosphere. It's not on any line, right, but they're going to call that 1 atmosphere. Okay, great. After, say, 20, we'll say 20 seconds, right, notice that we are dropping down. All right, so we've dropped down after 20 seconds, and now we have 0.6 atmospheres. Say right there. All right, well, at the same time, notice that the pressure of our NO2 has increased, right, up here to 0.8. We'll see, we'll give it a little X there. All right, well, continuing along, right, as the pressure of our N2O4 is decreasing, as it continues to decrease, then the pressures of our NO2s increase. And that's going to continue to happen until we reach equilibria. When we reach equilibria, right, notice that now the pressures don't change. Okay, and the reason that the pressures don't change is because the amounts don't change. All right, and remember that the amounts and pressures are directly related to each other by our ideal gas law here. And so, yeah, it's not that the N2O4 isn't still decomposing. It is. But at the same rate, it's being replenished by more NO2. And so we also see that here, right, that we now, these amounts or these pressures here don't change over time anymore. All right, so that starts off us how we're going to kind of establish our equilibria. Next up, we're going to look at something that we're going to call the equilibria constant that we're going to be calculating again for the next 5 chapters.